In the last few lectures, we've looked at a variety of different conjugated systems where we use double bonds to share electrons between different atoms and stabilize those molecules. Aromatic compounds are great examples of conjugated systems where in this case we're going to have an alternating series of double and single bonds connected in a cyclic ring so that we can share those electrons throughout our ring structure. This creates a very stable molecule, so we can then use these aromatic compounds in things like DNA, right, where we need a molecule that can stably maintain our genetic code over the course of our lifetime. So if we take a closer look at an aromatic compound, such as our benzene, shown here, if we draw this in our orbital hybridization, so each of our carbons here has a double bond, which means that it's going to have a p orbital here participating in pi bonding. So if I draw out my carbons here in my ring system, so I'm just showing the bonds between them as single lines, but now I'm going to have my p orbitals sticking straight up and down from each of my carbons. So with all of these p orbitals on each of our carbons, we can then overlap, which of course will make our double bonds. But then as you notice, you can see we have adjacent p orbitals on every carbon, so we can actually conjugate or share these double bonds throughout our entire ring. Right? So rather than just looking at it as 3 different double bonds and 3 different single bonds, we can actually look at it as a combination of 2 different resonance structures where we can share those double bonds around our ring. And in fact, all of our bonds are the same. We actually have a resonance structure here where all of our bonds are partial double bonds, and we have identical bonds between all of our carbons. So in our final ring system here, again, every carbon is going to be sp2 hybridized with our extra p orbital participating in that conjugated pi bonding system. And so, of course, with an sp2 hybridization, every carbon is trigonal planar. And that means our ring overall is a completely flat planar ring system. So again, because of this resonance here and the conjugation of our double bonds within our ring, our benzene is going to be more stable than comparable cycloalkenes. So if we take our cycloalkenes, and if we take a monocycloalkene, and we calculate the heat of hydrogenation to indicate how stable that is, and if we do that also for a cyclohexadiene with 2 alkene double bonds, we can predict approximately what the heat of hydrogenation should be for a cyclohexatriene, which looks like our benzene. Now, if we have this theoretical heat of hydrogenation for this compound calculated just based off of the heat of hydrogenation when we have isolated double bonds, we find a much higher heat of hydrogenation than what we actually measure for benzene. Again, this is because our double bonds are actually more stable than we expect due to this resonance and conjugation of our double bonds. So that difference in energy between what we can calculate theoretically based on the heat of hydrogenation of each of our double bonds versus what we actually measure is called our resonance in energy. So we have stabilization of our double bond through this resonance energy within our benzene ring system. So how does this conjugation and this resonance stabilization of our benzene affect its behavior? So, first of all, if we look at our benzene ring, again we have our conjugation throughout that ring system, which means that if we take a look at this from the side, right, so I take my flat ring and rotate it so it's perpendicular to the plane of my marker board. So here's my ring just as a flat line here. And above and below it, we're going to have all these p orbitals sticking up. And they create basically this cloud of pi electrons both above and below our ring system. So it looks something like this. Again, it's a very crude representation of it, but we're going to have our flat ring system with electrons kind of orbiting above and below it. So if we put our benzene rings next to each other with those clouds of electrons, we can actually get interactions between these orbitals, and you can get what we call a pi stacking interaction between our different aromatic rings. So even though our benzene is still a hydrocarbon, right, which means that we only have those weaker London dispersion or van der Waals interactions between our hydrocarbons, it will actually have higher boiling points than comparable molecules because of this extra pi stacking interaction. This is especially the case for larger aromatic ring systems. So if we take something like naphthalene, naphthalene we have two aromatic rings joined together. So here we have an even larger ring system, so when we go to stack those on top of each other, we're going to get stronger pi stacking interactions and an even higher melting point and boiling point for our naphthalene compound. This is also the case for our DNA as well. So in DNA we have these aromatic bases that stack on top of each other, and we use these pi stacking interactions to create a much stronger and more stable structure in that famous DNA double helix. So how does this conjugation affect the reactivity of our aromatic compounds? So since we have all of these electrons sitting in kind of this pi bonding system, our ring can actually act as both an electron withdrawing group, right? You can kind of take extra electrons and share it within that cloud of pi electrons, or it can act as an electron donating group. So it can take some of those excess electrons and donate them out to compounds that might need those electrons. So it's both electron withdrawing and donating, depending on the specific scenario that we're looking at. It can use those pi electrons to stabilize both kinds of reactions. So let's look at a particular reaction and see how that ring affects it. So let's say we have an aromatic compound and we have an alkyl halide attached just outside of our ring. Now alkyl halides, as we know, can undergo substitution reactions. Right? So my bromine right here can act as a good leaving group, and it can break off and form a carbocation. So we would end up with this carbocation right here. And of course, that's a tertiary carbocation. So this would react fairly well through an SN1 mechanism because of that stabilized tertiary carbocation. But how can our ring here affect this reaction? Well, if we look at that tertiary carbocation, again, remember that that's going to be an empty p orbital, and it can actually conjugate with the double bonds in our ring system to share that positive charge throughout our ring. We can represent that with resonance structures. So if we move that double bond there, we can bring that positive charge into our ring and move our double bond out. Right, so that's one resonance contributor. We can do that again. Move this bond over. And now we have our double bond over here. Our positive charge down here. And let's do that one more time. positive charge is over here. With one more resonance structure, we can move this over, and now we go back to our original carbocation. Now, if we look at all of these together, essentially what we've done is we split that one positive charge into 4 different positive charges, right? So our overall resonance hybrid structure would be sharing out 1/4 of that charge on each of our carbons as we're conjugating that carbocation through our entire ring system, right? So this is acting as an electron donating effect, where we're donating extra electrons to help to stabilize that positive charge. So in the end, with that carbocation more stable, that's going to significantly increase the rate of our SN1 reaction. Now, I do want to note, so what we saw with our previous conjugated systems is that those new possibilities would also lead to new reaction possibilities as well, right? So you could imagine our new nucleophile. Let's say we have a hydroxide ion acting as a nucleophile. And that could then attack our positive charge here, right? You might think, in order to create a new product where our hydroxide ion is adding on here. However, if we do that, what we're going to get is a new product that no longer has our resonance stabilized aromatic compound, right? So what we say here is that our aromaticity is lost. So we no longer have our alternating pattern of double bonds within our ring system, leading to that resonance energy stabilization. So we don't want to react in this particular fashion with any of the positive charges in our ring. So while we do stabilize it and increase our reaction rate, we're still always going to be producing our product where our nucleophile attacks that positive charge there to create our substitution site right outside our ring, right? So we say that the benzylic site, that site adjacent to our benzene ring, has increased reactivity, but we're not creating any new reactive sites within our ring itself, right? We always want to retain that aromaticity where we get our extra resonance energy stabilization. So we're always going to be attacking here with our nucleophile, whatever that looks like, and we're not going to be attacking at any of these other possible positively charged sites within our ring. The end result of this here is that our SN1 rate will increase at those sites adjacent to our benzene ring. So our SN1 rate increases. Our SN2 rate will actually also increase. So even though our SN2 reaction doesn't use a carbocation intermediate, it does have a transition state that involves a partial positive charge on that benzylic carbon adjacent to our ring. We can still kind of share that electron density with that partial positive charge and increase the rate of reaction for SN2 as well. So an SN2 reaction, of course, would be preferred when we have a less substituted carbon. And in this case, we'd have a very high rate of reaction for that leaving group attached to our benzene ring, because again, we'd be able to help stabilize that transition state as our nucleophile is attacking. Now let's look at another scenario here for the reactivity of our benzene ring and our adjacent benzylic groups. So in this case, we have a benzylic hydrogen, or a hydrogen adjacent to our benzene ring. And of course, when we have hydrogens, we can try to remove them with bases. So if I add a strong base here and take off this hydrogen, I'm going to create a carbanion, a benzylic carbanion, adjacent to my benzene ring. Now normally, of course, with alkanes, they're very weak acids, and it's almost impossible to deprotonate this, right? Because our carbanion is very unstable. But in this case, with our ring, again, that carbanion is going to be in a p orbital, which can be conjugated with our ring system. So similar to our double bond, this can get shared into our ring. So in this case, this is an electron withdrawing effect because we're pulling away that extra electron density. So now we move it down here, create a lone pair there. As we created our double bond outside of our ring, again, we can continue to move that around. We move it over, make a new double bond, move this over, make a new lone pair. Here's our new lone pair, there's a new double bond. Move it again. And one more time to get back to our original carbanion. Again, we've been able to share that negative charge and the instability that's associated with that throughout our ring system, right? We moved it jumping from carbon to carbon. We have 3 different positions for where that carbanion can sit within our ring, in addition to the 4th position up here. So essentially we've split that out 4 ways to help to share that burden and that instability there, right? So that means that our hydrogen here actually becomes more acidic. So benzylic hydrogens are more acidic because that carbanion has that resonance stabilization, right? That's one of the things that we learned when we looked at acids at the beginning of organic chemistry. We said that resonance stabilization of the conjugate base increases the acidity of our compound. So overall here, we can say that the acidity of our benzylic groups, our benzylic hydrogen in this case, will also increase just like our SN1 and SN2 reactions. Or really what's happening here, right, is that our benzylic carbocation is stabilized and our benzylic carbanion is stabilized. Now the final example that we'll look at of our benzene ring stabilizing an unstable intermediate is in a free radical reaction. Right, so if we're doing a free radical halogenation of an alkane, so we would create our bromine radical, and this would come in then and pull off a hydrogen from our alkane region here, and it then ends up producing a alkyl radical. Now in this scenario here, again, that alkyl radical is going to end up right next to our ring. So we have this new radical here, and once again, that radical sits in a p orbital, and we can share that with our ring system. Right, so we can come in here, share our free radical up there with multiple different resonance structures. So our first point, we have the radical there, double bond up here, and again we have our multiple resonance structures where in each case we're able to move that free radical around our ring. And with our final electron movement, we're able to bring it back to our original structure. So if we perform free radical halogenation with our benzylic group, we're always going to end up creating that free radical next to our ring, and then of course eventually adding on our new halogen next to that ring, where the radical intermediate is stabilized by the electron withdrawing into our benzene ring system. Again, we're not going to add on our halogen at any of these points within our ring because that would break the resonance stabilization within our ring system, right? We would lose that resonance energy. So we want to maintain our aromatic system, but we're still able to stabilize that intermediate and help our bromine to add on there right next to our ring system. So any kind of free radical halogenation is always going to be selective for that benzylic position right next to our benzene ring, where we can stabilize that intermediate. So again, our free radical halogenation reaction rate is increased. Now again here, of course, as with our free radical reactions with our allylic group, we're commonly going to use NBS as our source of bromine, just so that we don't have our actual bromine molecule here, which can potentially react with our aromatic ring in other ways. Right, so we'll use that just as the source of bromine for our free radical reaction, but the overall reaction pathway will look very similar to with just our plain bromine here. So as we've seen, our benzene ring can affect the rates of a lot of our familiar reactions through that electron withdrawing or electron donating effect of our conjugated pi bonding system. Now, these same effects can also lead to some interesting new reactions as well. So we're going to quickly go over the benzylic oxidation reaction. So this reaction uses a free radical mechanism. So we're going to use a benzylic hydrogen to make a free radical adjacent to our ring. Right? So this guy is going to break off, and then we end up creating a free radical there, which of course is stabilized by our ring system, and we're going to use that to oxidize these carbons right outside of our ring and add on new oxygen bonds there instead. So our benzylic oxidation reaction is going to proceed through that stabilized benzylic radical intermediate, and then we're going to add strong oxidizing agents to break our carbon-hydrogen bonds and our carbon-carbon bonds even, and add on new bonds to oxygen. Right? We're always adding bonds to oxygen when we're oxidizing compounds. So we have a couple different agents that we can use for this. So we can either use potassium permanganate with water. So this is a very strong oxidizing agent. We'll see it used for a variety of different oxidation reactions. And then in a second step, we would use an acid, such as HCl, to protonate our final product. Alternatively, we can use our chromic acid, which can be produced through a mixture of a chromate salt with our very strong sulfuric acid in aqueous conditions, and this will be with lots of heat as well. So both of these are very strong oxidizing agents that will use that free radical intermediate, again, to add on oxygens here. So our product here from this benzylic oxidation reaction is going to be our benzene ring. Again, of course, our ring is maintained since we have that extra resonance energy stabilizing that, so we generally don't want to break our ring itself. But now we're going to take our carbon over here that had our benzylic hydrogen, and we're going to take all the original bonds that we had. So here this carbon had one bond to a carbon and two other to hydrogens. Right, we have two hydrogens and a carbon here, and we're going to replace all those bonds with bonds to oxygens. So now our three bonds become three bonds to oxygens here, and we actually completely lose that carbon at the end. So that's likely released as carbon dioxide during this oxidation process. Now on the other side, we had carbons over here that we have to deal with as well. But if you'll notice, this carbon here is just bonded to three different carbons, and we have no benzylic hydrogens, no hydrogens here that are connected adjacent to our ring system. So without that reactive hydrogen there, we actually won't react with this side, and we'll end up keeping that same carbon structure over here. Right, so any carbon structures that are on the ring that have benzylic hydrogens will be converted to our carboxylic acid here, whereas any carbons that don't have those benzylic hydrogens will still stay the same as before. Right, so if we look at another example here, we could have a structure like this, and if we add in, I'll go ahead and use our potassium permanganate in aqueous conditions with an acid to follow it up, and this will produce Now in this case, a dicarboxylic acid, since both of my carbons have free hydrogens adjacent to my ring, both of them end up getting chewed up to make our carboxylic acids. And again, our ring stays the same as we seek to retain that aromaticity and retain that extra resonance energy stabilization there. So this reaction is a very useful way to convert relatively unreactive alkyl groups on our benzene ring into these more reactive carboxylic acids, which we will be talking about these in more detail later on in organic chemistry. So what we've seen here, right, is that our aromatic compounds have this extra stability for themselves with this conjugation effect, but the stability can also be used to help a lot of different unstable intermediates in a variety of different reactions. This will speed up some of our very familiar reactions while also allowing completely new reactions through the stabilization of those unstable intermediates. So these are very important compounds for our organic reactions because of the wide variety of different reactions we can do on the outside of our aromatic rings.